Hey everyone, it's Will. Welcome to miniKanren uncourse hangout number 21. Today we have a special guest, Rob Zinkov, who is at Indiana University, where I got my PhD and spent about 10 years. And Rob has been doing lots of cool work with something called probabilistic programming. And there's a sort of a new class, a new generation of probabilistic programming languages that are very interesting and hot topic right now. Rob works on one of those languages called Hakaru, which I think he's going to maybe talk a little bit about. And we've been working together on and off on a prototype for a language called probKanren, which is a probabilistic programming extension to miniKanren. So hopefully we'll get to see a little bit about that also. And we'll just see. So, Rob can talk about whatever he wants, and he can go for as long as he wants, and then we will hopefully ask lots of good questions for him, and we'll go from there. And if he ends early, then we'll do traditional miniKanren stuff. So whatever. We'll just play it by ear. All right. Rob also is known for his comedic talents also. So maybe he'll talk about that a little bit. Okay, here we go. Without further ado, here is Rob Zinkov from Indiana University.
Thanks, Will. Thanks for the nice introduction. All right, so I kind of want to talk a little bit about kind of my background, because in some sense it motivates why I explore probabilistic programming, which might be a little bit different than why other people might explore probabilistic programming, or even the motivations with logic programming.
I just have to mention that in chat, people are talking about your yo-yoing expertise. Yeah,
Right.
I know you mentioned yo-yoing before. Okay, so before we start into the technical stuff, can you give us a yo-yo demo?
It would have worked better if I actually landed it.
And we also can see your chair. Is that an Aeron chair?
That is an Aeron chair. I got it for 200.
Whoa. My chair is like a bunch of bricks.
Nice.
Yeah.
Oh.
Not. Yeah. Well, okay. So,
Right.
so we know Rob is into yo-yoing.
All right.
All right. So sorry, didn't mean to distract you. Please.
No worries. Also, I think there's a bit of a glare on my screen, so let me just. All right. So most of my motivation with exploring probabilistic programming actually comes from machine learning, which can be seen as a sort of program induction, in the sense of almost all machine learning problems can kind of be seen as you've been given the input and output of a program, and you'd like to infer the program that created it, or the best program you can do. And this is actually frequently how machine learning is phrased when it's taught in classes. They say traditional programs are programs where you give me an input in a program and I give you an output. Machine learning programs are such where you give me an input and an output and I give you a program. I think I'm not completely clear how much this perspective has been brought out. But certainly, like with miniKanren, it's kind of the same thing. It's you give me a program, you give me an input, you give me an out. I can give you an output, but if you give me an output, I can also give you an input. This is kind of a lot of the style of miniKanren programming, and a lot of this style kind of pervades probabilistic programming as well. Kind of the fascinating thing is that this is really almost all machine learning problems can be phrased somewhat in this way of there's this program we don't really know, but we have data that this program produced and we'd like to find it.
So for those who are maybe not very familiar with machine learning, can you just maybe give a little sort of broad overview about maybe what that field's about, the types of machine learning that people might encounter, and so forth? Is there like a 30,000-foot view of machine learning that you can give us?
Um, it's not so. I mean, broadly, the kind of what machine learning problems kind of look like is they look like I have some phenomena, and I have some data from it. So just I feel like the 30,000 views not particularly helpful because there's so many different approaches. But I will say, like the way machine learning problems largely look, at least to people from the outside, is I have some data. I have some data about, say, like you're trying to predict the weather. So I have some data from like things like barometric pressure and different geological properties, and I have things like it rained, it was cloudy, etc. And these can all be kind of combined together, so that in the future, when you see things like different like barometric pressure and like wind velocities, you can predict future weather phenomenon. And it's a similar kind of thing of we can predict weather. So almost all machine learning problems have this facet to them. So we can predict whether a document is spam or not based on the word choices that were used, because historically certain words are associated with being spam versus legitimate email. A similar thing for there was a recent article on troll behavior. There's a particular pattern that you can kind of see over and over again. And a lot of machine learning is these particular patterns. They get called. There's a word that's called features. And so you can, in some sense, count how often different behaviors are indicative of, say, trolling activity or spam, and then you can essentially make what's called like a threshold, and say, well, for at least for trolling, it's like you've been argumentative, you've been posting very frequently, the IP address you've been posting from, multiple things from the IP address have been posting frequently, so probably a troll. So a lot of machine learning kind of has that kind of flavor of we're going to take these indicators. Frequently people say, how would I find these indicators? Where would they come from? The answer to that is that it's very much an art, and it's very much domain expertise.
And if you get the wrong indicators, what would be the problem? Is the problem that you just wouldn't have very good predictive power, or it would take too long computationally, or both? So what's the trade-offs there?
So, for the most part, you just don't have predictive power. Your prediction algorithm ends up being no better than a random coin. Just ends up being no better than a groundhog, as I've said in other lectures I've given about this. Computational powers tends to be more a consequence of what you choose to make your patterns detector. So if say in the troll example, whether to analyze whether someone's being argumentative, you have to run a program that takes a year to run. That's really where more your computation will go. For the most part, these how long these things take to run is linear in the size of the data, and you try to make your feature detectors run pretty close to constant time, if you can get away with it.
So my understanding then is that machine learning, when I think of machine learning, I think of large data sets and also noisy data sets, right? Data that maybe not perfect. Do you think that sort of goes with the territory?
Oh, of course. In some sense, for me, I consider the noisiness a strength, because in some sense, noisy data means I'm only obligated to give noisy answers.
And this is sort of the opposite of miniKanren, right? When you write a miniKanren program, if you get one rule wrong, then like the whole thing just doesn't work. We have like no tolerance for noise at all in traditional miniKanren.
Right. I mean, I consider noise just intrinsic to problem domains. And noise comes in different characteristics, It's everything from noise in the sense of like your sensor readings are a little bit inaccurate, all the way to just someone just fat fingered the data. So I'll just kind of give an anecdote. I have a friend who works with data on different drug rehab responses. And one of the fields they have is the age. And the age, these are teenagers, but you occasionally get teenagers that are of course 117 years old. Which is of course that's just how the data comes to you. And you can of course clean it through some kind of hand mechanism, but you can also just have a kind of assumption that, well, there really aren't 117-year-old teenagers, and the person probably just hit the one key twice.
So how would you encode that knowledge that the age is going to be, 14 to 20 or something like that?
So personally, as someone who does probabilistic programming, I would encode it as a certain range. I would encode it as a range of values. I'd say teenager, someone from 13 to 18, just continuously.
And is there some notion of noise? So if you said 13 to 18 and you got an age of like 20, would that be kind of okay, or would the system try to throw that out, or does it depend?
If I made it a continuous range from 13 to 18, in some sense, getting an age of 20 is an error. Like it just has to be thrown out. I could also have something like a bell curve going outward from, say, 15. The trouble with a bell curve, of course, is that bell curve also says things like -5 are a very valid age. And of course, ages all the way up to infinity, or just 10,000, 50,000, geological ages are, if extremely improbable, still perfectly valid. And I do want to kind of say, with when you're working with like these what they're called probability distributions. They say how the values are distributed over these different ages. There is a distinction between ages that are improbable. I was just reading the chat. There's a distinction between ages that are improbable and ages that our system has said are impossible. So
let me ask Margaret's question. So Margaret was saying that she's got a friend who works in one of these large telescopes, and part of his job is writing programs that remove noise and leave signals and space images to try to get distant information about distant planets. Maybe this is like the exoplanet discovery. And she was wondering if that would fall under machine learning.
It depends how this noise was removed. I would argue that whatever technique your friend is doing is almost certainly machine learning at this point in time. But there's a lot of like what people will call machine learning is if like there was some data involved. But if there was a person kind of just handwritten the filter, I'd be a little hesitant. But I'm almost certain that at least the way, from what at least my friends in astronomy do, they're almost certainly using machine learning to accomplish this task.
And is that just because the data sets are so large, or is that because the machine learning can actually be more accurate than a human?
It's actually it tends to be because a machine can be more accurate than a person, because you can always just filter the large data sets down. In some sense, what's actually very interesting with a lot of like when data sets actually get very massive, a lot of the inference methods actually get simpler. They they do a bit less. And also, there's always the option to just throw out all your data. You can always turn a large data set into a small data set by just cleverly throwing out data points.
So I've got a friend who works on Google Translate, and he said that largely it's just because they have access to all of this language information on the internet that they can use relatively straightforward statistical and machine learning methods because they have vast amounts of data for English, let's say, and that it's just how much data they have is really important. Whereas if you have a language that doesn't have much information on the internet, it becomes way, way harder because the data sets are smaller. Is that a general trend you see with machine learning?
It depends on the problem. It really depends on the problem domain. In some sense, what happens is when you don't have data about a problem, you really have to guess well what unseen So when you think about something like natural language, when you don't have a lot of sentences, you really have to guess well what sentences will look like, because so much of the data you're going to be predicting could be radically different. And in some sense, that guess really factors in a lot more heavily. When you have all spoken language on the internet, all written language on the internet, at that point, you don't have to guess as much because your data, in some sense, really lays out the space well. So you can kind of just get out of the way and just try to use a method that goes through all of that. Effort spent on a good computationally expensive guess doesn't pay off as much if merely making sure you use all the data will probably put you in the right ballpark.
I was reading yesterday that with some of the machine translation efforts, they're making efforts on languages that the machine learning experts don't have to be able to speak the language at all, right? So the techniques are largely independent of the language. That if you have enough data, that even if you don't speak the language, you can make a reasonable effort at translation. Does that sound accurate?
It's actually very interesting in the sense of the way translation is done, the way the translation models are done. So I think the best ones, really, you do benefit from having understanding of the languages, because some of the if you want to make a specific, say French to English, or say something like, I don't know, Tamil to English. There are particular features of the language that become very important, and but for the most part, actually, what a lot of the way machine translation problems are posed is they're actually posed almost like code cracking. So a lot of the machine translation logic is the same math that would go to me and a friend are communicating with a secret code you don't know, and you're gonna try to, and there's an algorithm to crack that code and turn it into English. And as far as the math is concerned, that code can be Pig Latin, it could be French. It's the same technique. With, of course, converting the secret code of French into English involves a more sophisticated encoding algorithm. And that encoding algorithm, in some sense, becomes a translation. It's the same math fundamentally. And the way a lot of these systems work is they're saying this phrase in this coded language corresponds to this phrase in this English language. And in fact, a lot of these translations is about kind of mapping these phrases onto each other.
Daniel has a comment that Google had a pretty cool spell checker based on n-gram probabilities similar to their translation approaches. For example, Iceland is an IC land, so it would be automatically corrected to Iceland is an island. Not super sophisticated, but with lots of data, it works pretty well. And I think one of our mutual friends, Alex Rudnick, works on Google Translate or has worked on Google Translate, and he's made that clear. Like when you have enough data, some pretty straightforward approaches can work better than you might think.
Right.
Uh,
Well, this is also why Alex is so interested in like indigenous languages, where there really isn't, it's like when you have 1,000 people or less speaking a language, there's only so much data you can get.
yeah, exactly. Okay, so going back to what you were saying towards the beginning about sort of program induction or learning a program, or so you were making some connections between sort of the miniKanren stuff where we run programs backwards, right, and the machine learning approaches. So one thing you were saying in the machine learning, if I understand correctly, that you were inducting programs. You're actually learning programs, not just inputs and outputs. Is that correct?
That is correct.
So would that be similar to the sorts of things we do with our relational interpreter, where we are trying to learn a scheme program or a racket program based on a query?
I mean, I've always been of the impression that you don't need to actually make a relation. You don't have to necessarily embed a relational interpreter into something like miniKanren to get that far. Even in examples such as even like Appendo, I would argue that you already have a program that goes from appended lists to separate to two lists that can be appended. I don't think you need a relational it's kind of already buried there. Yeah.
Sure, because the relational interpreter it's just a miniKanren program, just like Appendo. I guess the thing is, in my mind, and maybe I shouldn't make this distinction, but to me, inferring the input lists from the output lists, it feels different to me than learning scheme code that's executable, even though it's underlying, under the hood is exactly the same technique, right? It's the search-based technique and constraint solving, right? It just it kind of feels different to me because your programs, you're learning possibly recursive programs that are arbitrarily complex. Of course, the running time goes up very quickly, right, when we try to do that stuff. So in the machine learning, so would you consider something like Appendo learning the inputs from the output? Would that be something similar to machine learning? Is it mostly just the same goal but different techniques, or is it sort of have a fundamentally different feel or goal?
I mean, So David just said the program is stored in the constraints. That is exactly the point. Yeah, I do want to kind of yeah. So the point David's making in the chat is completely valid. You can reify that into a scheme program. I would argue like run or something like run could have been rewritten that basically when the query is run, instead of you producing all the answers, you produce a program that when runs would give you the answers. And I think that's very much in the spirit, at least, of what I see. I mean, machine learning, the techniques are different. Search isn't used as much because search is so expensive. Search is a very expensive thing to do. Search is almost like the method of last resort, because it's just like it's an inch above brute force, but it'll kind of be brute force in the limit. I think a lot of modern machine learning prefers to do something much more directed, something, maybe a greedy search, maybe dynamic programming to save computation, or at least what I'm very partial to, these kind of gradient approaches where what you're searching through has some continuous properties, so you can kind of use that information to kind of direct your way toward an answer. Also, one of the big features in machine learning that's kind of absent from at least things like search is a lot of search problems is this notion of the best answer. In Appendo, there's no really best answer. They're all kind of the same. They're all kind of they're all equally valid. In a lot of machine learning problems, there really is the best answer. So when you think about things like machine translation, if I give you a piece of French, there are multiple valid translations into English. So bonjour can just someone probably means hello from that. But if a translation system replied salutations, you wouldn't say it was wrong, just not an ideal answer.
Or Daniel says good day would be the most literal, maybe.
Right.
So going back to the miniKanren, I think that's a good point. With the Pendo, all of the answers are sort of equally well. And when we run the relational interpreter backwards to generate scheme programs, we have this issue of, where there are infinitely many scheme programs that evaluate to 6, for example, and some of them just are absurd because it'll be like lambda x, lambda y, lambda z, lambda w, lambda v, and then 6 is the body, right? Applied to a bunch of nonsense. So we have these lambda expressions or scheme expressions which are really complicated, and they build up all these arguments and ignore them. And to a human, they kind of feel stupid, but we don't have a way in miniKanren search to avoid it. The other thing with miniKanren search is that in general we're using as a theorem prover, so we are doing like exhaustive search. We want to try to prove that we got every answer and that no other answer exists, right? Which I guess in machine learning, if you're only concerned with the answer, you might not have to do all that work.
Right. So this is something certainly in Will Mai's discussions before, kind of off camera, we spent a lot of time talking about like, well, will this method find all possible answers? And from the perspective of Will miniKanren, that's very important. From completeness sense. From the perspective of someone who does machine learning, is like, I don't care. I want the best answer, or say the top, the K best answers. So a method that kind of removes large parts of the answer space isn't that big a deal for me. So I see a question here: is there a line between machine programming versus tuning parameters for an existing function? So I'm going to assume machine programming means program induction. And in some sense, I would argue not. In the sense of, I feel like so if we think about things like generating miniKanren programs, I could argue that we can kind of we can have a parameter for which clause we should invoke when kind of expanding out sub-expressions, and that can kind of be used to choose which miniKanren program gets created.
All right, very good. So that's a nice overview of sort of what machine learning is about, and some of the issues that it touches on, and some of the applications like natural language processing or cleaning up astronomical data or weather prediction or so forth. Any more questions about general machine learning before maybe we could talk a little bit about some of the probabilistic programming languages? All right, ready for the main course, Margaret says. Good.
All right.
Yeah.
All right, so allow me to share my screen okay. So I kind of want to talk about.
I'm not seeing the screen yet. Anyone else seeing it?
You don't see a screen?
Nah. Oh, Margaret sees it. Okay, hold on.
Okay.
There we go. There we go. Yeah, we're good. Okay.
All right, cool. So let's talk about. So let's talk about how you might say write a program that gives you possible answers for a coin. So I can't really see the chat right now, Will, so you'll have to.
Yeah, I'll let you know if there are questions. So we're going to model a coin flip. Is that right?
Right.
Okay.
So how might that get written in miniKanren?
Okay. So this is the interactive part. So how might we model a coin flip in miniKanren, given the miniKanren we know? Any thoughts on that? Okay, Orchid says we could define coino side. Okay.
Coino side?
Rob, can you move your window a little to the? Well, no, I guess it's okay. Okay. Define a function called coino that takes
Okay.
an argument called side, and then the body is going to be a kandi,
Okay.
and it's going to have two clauses. One where we unify side with quote head, and one where we unify side with quote tail.
Okay.
Or tails.
I'm writing this correctly. Okay. Right. What did I do wrong here?
All right, let's see. You need extra parens. Okay. Yeah.
Yeah,
There
all
you
right.
go. There you go.
All right, let's see. All right, heads.
Okay.
Seems good. We can have more answers. Tails. All right, more answers. No. All right. So we've modeled the heads and the tails of a coin, and how might we actually do a bias coin?
So we want to model a coin where maybe heads is more likely to turn up than
Right.
tails.
Yeah. Suppose heads is likely to show up more often.
All right. Daniel says more than one instantiation of one of those clauses.
All
Okay,
right.
so say it's twice as likely to get heads as tails.
Right. So suppose now we do this. So okay. Heads, tails. All right. So in some sense, we get all these answers, and now heads. So now we can kind of move between them, and if we collect up these answers, I guess in run star. Is run star available from Veneer? I'm trying to remember.
David said it's not.
Okay. All right.
Just click the more answers.
Okay, that's fine. So we'll just in some sense, if we're running miniKanren, we can run star, collect up all the answers, and we'll have all these choices for heads, and tails. And we can kind of keep doing this, and this is a bit hacky. Is there something else we can do to kind of like just encode our bias a little? How might we go about, say, encoding the bias that doesn't involve just adding clauses?
Orchid says, I don't think we can do it in miniKanren. And Daniel says we could create a cond P in miniKanren with an explicit sampling bias. So the cond P is a probabilistic condi, where you explicitly assign a probability to each condi clause by hand.
So maybe something like conp and say so you're proposing maybe something like this?
That's right, and we have implemented this before. Yeah, Dan and I showed a conp in a talk once, and it's actually quite easy to add this to miniKanren. It's not hard to implement this.
All right. So this seems all right. Um, what are some things this conp can't do?
Daniel says it can't sample, whatever that means.
Well, I mean, in some sense, yeah,
Or not
neither can
repeatedly.
run. So go on.
He says not repeatedly anyway. Can't repeatedly
Right,
sample.
it can't really sample. Um, is there anything else that like we really can't do with this approach?
Or I guess more generally, like, what are the disadvantages of this approach?
Right.
Would you be happy writing a big application using this approach?
Right.
Daniel says the weights are programmer provided. Yeah, so where do these weights come from?
Right. Well, I mean, the question I can always, but then you can't, I suppose you can always just have like things like, perhaps these could be logic variables and things like that, unified against.
Yeah, I don't know if we support that one.
Okay, all right.
Orchid said, I think it doesn't run backwards, right? And Daniel said there's no facility to learn them with this approach.
Right.
And Orchid said the probabilities are ignored, that basically there's no Bayes' law, whatever that is.
Right. Well, yeah. So the key thing is that in some sense these weights aren't really they're not really like. So I don't know how conp was implemented.
It just had ground probabilities, like those had to be ground numbers.
Right.
So 0.6, 0.4, whatever.
You're not allowed to make them logic variables.
That's right. And when you hit the conp, basically you would call random. You would like roll a die and then pick one choice and commit to it and go down that branch. And then upon backtracking, if you failed, if you hit the conp again, then you would roll the dice again. But it was pretty naive, and it was hard to find answers that were deep in the tree. Also, you just didn't have a very high probability of reaching.
Right, because you have to get there first. You don't really start there.
Nahal has a good question. He asks if run star produces an infinite number of outputs in this program. And I think I've implemented conp at least two different ways. One way, it tried to calculate probabilities and output the probabilities with each answer, in which case it would give you a finite number. But the other approach, which is just more flipping the coin as you go down, that I think actually would give you an infinite number of possibilities if you did a run star.
Right. So here's a question. I'll ask people. How might we implement the example of so let's just say, how might we implement the example of the different teenage ages where we have a range? How might we do that with conp?
So we want to be able to generate a distribution or a range of ages? Is that the idea?
Right, a range of ages.
Any thoughts? Daniel said, without finite domains, that's a little unhappy. A bunch of conv clauses. I think FD means finite domains, right?
Yeah. Right. What about real domains?
Real domains. What's a real number?
Okay, fair enough.
What miniKanren support for real numbers is sorely lacking.
Hmm. Um.
Whole link type encoding of IEEE 754S, Daniel.
That's kind of cute. Embed IEEE 754, 854, like into
as,
miniKanren, just like schemas.
as Oleg style little Indian binary numbers.
Nice. Guess we can kind of do that, and judicious use of conp. So
Well, Daniel's point is good that we really don't have much support for real numbers or anything like that in traditional miniKanren.
right. Um. So in some sense, when I first encountered miniKanren, and I asked people how it did like kind of probabilistic stuff. This is something like this essentially was what different people at Indiana University presented me to. Um, and of course, for some of the objections that were kind of brought up now by all of us, this isn't ideal. It's not bad though. I think if you have stuff like finite domains, and your domain isn't too like gigantic, this approach with a little bit of post processing, I think, is probably fine. But it does run into problems.
So,
So
so can you think of like a little small problem that you think we could handle with this approach? Was sort of like the conp approach. Is there a fun little problem that be possible to express that way? That's interesting.
um, so I think like simulating things like dice outputs, I think you can still do with something like conp pretty cleanly. Um, whereas say you have something like a five-sided die, and you have something like
So maybe we could do like a Yahtzee program or something.
right. So we can do a Yahtzee program and kind of simulate Yahtzee games, or anything with kind of discrete motions. And it doesn't have to just be the die. It could also be different movements because movements are also finite, finite domain. So um, we can simulate plays from the game Candyland because Candyland is completely deterministic given a particular shuffling of the cards. So
Yeah, I learned a long time ago you can't actually throw a game of Candyland if you're playing against a kid, no matter how badly you're trouncing them.
right. Yeah, my understanding though is that it's a completely deterministic game, given the initial cards. There's nothing you can do. It's once the game starts, the outcome has already been decided. No one knows quite yet what it is, though.
I was volunteering at a children's hospital years ago, and I made a mistake of playing Candyland with these poor kids, and I was just like crushing them. I couldn't like throw the game, right? There was like no way to do it.
Oh my. All right.
Okay,
So
so we're gonna see now like a better way to do it.
right. So me and Will have been working on a thing called probKanren, which is a probabilistic programming language. And in some sense, I feel like probKanren kind of captures another way of doing these things. So just like this. I just wrote this just to make sure that I knew how to write this in miniKanren. Um, so can everyone see the screen all right?
I can see it fine. Yeah. Yep, everyone can see it.
All right, cool. So let's do so ignore what's on the screen right now. I just wanted to make sure that probKanren would run what I wanted it to run. So what we've written is we've written a different run function called runmh, stands for Metropolis Hastings. And here we've added a few primitives. So coin flip is typically called in probabilistic programming languages, flip. And flip takes its bias and then what the outcome of the coin is. And because coins are heads or tails, we, for convenience, will just use Boolean values true and false, because that'll work just as well. So we can sample a coin with 50% bias. And in fact, if we ask for multiple solutions, it's not going to just give us 2. But instead, we'll just keep giving the coin. So in some sense, run could be made to act more like a sampler.
So what would happen if you were to do a run star?
Do we have run star?
Probably not. I hope not.
Well,
run star, I think this goes back to Nahal's question, right? About if you did a run star, would you get infinitely many answers? And
all right.
So we didn't even bother defining run star because you could flip the coin infinitely many times, right? Or an unbounded number of times. So,
right.
So run star in this formalism doesn't really make sense.
Right. So to answer Nahal's question, in some sense, run star in this formalism would return an infinite stream. We can just keep getting answers, as many as we want. And then, it would be ill-advised to maybe say, call run star and just have it flood my screen. So in this situation, we can, in some sense, represent probability distributions as these relations. Now, make a biased coin, say something that's biased toward tails 75% of the time, we could just change this argument. Hold on. I should probably go back to run MH. Let's do that. And you'll see that there are more trues than falses. In fact, I can make this bias even larger to make it a little more clear.
Orchid asks if this is Hakaru.
No, but I will be introducing Hakaru. Well, I'll be introducing an older version of Hakaru, because the newer version, while it can do more cute tricks, I think it's a little harder to use.
So what language is this then?
This is probKanren.
This is probKanren. It's on my GitHub. If you dare play around with it.
If you dare. So probKanren, I'm going to basically be using the parts of probKanren that work. There are parts of probKanren that don't work right now, so that's why I kind of don't want to be freewheeling. So what will actually happen is once we start touching the parts of probKanren that don't work, I'm going to, in some sense, I'm going to switch over to Hakaru and keep writing those kind of programs. Note that this isn't like an intrinsic limitation in probKanren as much as we just haven't gotten the bugs out. The formalism can support what we want to do, it just the bugs have to be removed. So one thing to, of course, note is that we don't have to just have a finite domain now. We can do something else. The question I ask for people is, what do you suppose this program does?
Any thoughts? Daniel says it gives 20 real values between 0.0 and 3.0 with a uniform random distribution.
That is correct. The question I ask for people is, what does it mean for something to be the uniform random distribution?
Daniel says that's just again. Is that what it does? I thought it did something different.
No, that's exactly what it does.
Oh, all right. Well, I thought it was like centered at 0 with a standard deviation of 3 or something like that.
That's another distribution.
Oh, okay. So Daniel knows it better than I do already.
All right. So yeah, this is the uniform distribution. Um, of course, with 20 values, that can be a little harder to see. And in fact, it's very hard actually to really get a feel for what distributions do. So typically, I feel like probabilistic programming is one of those things that's actually very hard to do from the command line. I feel like you almost need something very visual from the get-go, which is
Can we do something like take the mean of a 1,000 samples or something like that?
yeah, of course we can. So Will and I have defined primitives like mean. And if we make this larger, you'll see it eventually approaches, fingers crossed, 1.5. All right.
Ah, okay. 20,000 samples. How high can you go for a source skin slow?
Well, that's what I want to see now.
Our implementation is not efficient. Let's just leave it at that.
All right. So I hope that now that I made it large enough, you can kind of see it kind of oscillates around 1.5, which is the average value that would come from this distribution. So going back, one thing that's kind of particularly interesting though here is that we're not really talking about probabilities. We're talking about things that with different probabilities can have different values. So we don't talk about there's no number uniform 0, 1, 3. It's that Q can have different values between those values, and different ranges can have us. So the probability that Q, so the question I'll ask, so the probability that Q will be between 0 and 3 happens with what probability? What's the probability that the value will be between 0 and 3?
Daniel says the probability is 1.
Right. Stated another way, 100%. Here's another question I can ask. What's the probability the value will be between -10 and 10?
One also.
Yes, that is correct. Also 1. And then, of course, what's the probability it will be between 0 and 1.5?
1/2.
Exactly. So in some sense, probabilities are really questions about the domain, kind of the domain of values you'll have. So basically, different chunks of our domain we can take and assign a value to them. It's not particular elements; it's actually particular ranges of the space, because we don't particularly care about elements. We care about subsets of the domain of values we can have. So, and different distributions allow you to have that. So, of course, flips. So, what's the domain of uniform?
I think I miss. Oh, okay. So Nahal says it's 0 to 3.0?
Yep, that's the domain.
Yep.
What's the domain of flip?
Margaret says 0 to 1?
Is that the domain of flip?
So are you making distinction, or are we using these terms like domain and range? So I guess from like a math function, the domain would be 0 to 1, but like the output. Well, I guess if we're talking about the probability in the first position or the Q. Are you talking about the Q?
I'm talking about the Q.
Okay, so whatever metaphoric output ranges over?
Right. What's the domain of Q? What values can Q take?
So the first number to flip would be 0 to 1, is that right?
Right. The first argument it'll take 0 to 1.
Okay, and then for the Q in this case, what values could we have? Nahal said hash H hash T, I guess it's heads and tails, which
Right.
we're representing as true and false.
Right. I guess another argument I can say is since there was this kind of confusion, what values can this take? The first argument to uniform.
Orchid says real numbers.
Yep. And the second value?
Also real numbers. So
Right.
could uniform be negative? Or sorry, could the first argument to uniform be negative?
Is that your question? Yes. So
That's my question.
right. Yeah, of course.
And what would happen if the first argument were smaller than the second argument?
Well, the question I ask is, what's the domain of Q?
Okay, any thoughts? I really don't know what it's going to do.
I actually don't know what it's going to do, but at least mathematically we can.
Yeah. Nahal says we're going to get back the empty list. I can imagine the empty list. I can also imagine an infinite loop. Let's see.
Well, all right, fair enough. The empty list is the right answer. probKanren doesn't do domain checks.
Oh, okay. So it's taking the difference between them, and that's why we're getting.
Yeah, exactly.
Okay. All right. Put that on the bug list.
Yeah, I will. All right. So, of course, something interesting, of course, we can do is we don't just have to. We don't have to just like have. When we have these variables that can range value over different domains, we can still use them just like any other logic variable. So
you want to introduce an X?
I want to introduce what? Yes.
Fresh X, yeah.
All right. So the question I have is to everyone is, what does this program do?
Daniel says it creates 10 randomly biased coins and tosses them.
Yep. That is what it does. Is the bias the same for every coin?
Possible but unlikely, says Daniel. And Nahal says, you tell me.
Well, the question I have is,
Margaret says, I think no.
so the question I have is like, how can we check?
Oh, that's a good question.
How might we check?
Orchid says you can't. Nahal says, run it again, Sam.
Did that help?
Orchid says, equal to the original program. Nahal says, yes, it helped. Okay, so Nahal, did you figure it out? Bias is the same, he says.
So how might we check?
That's a good question. I don't know. Any ideas? How do we prove Nahal's theory is right, or how do we gain evidence, collect evidence that Nahal is right, that the bias is the same? Marcus says, well, you can make huge lists, okay. And what would that tell you with the huge lists? Estimate the bias from the huge list by counting.
Well,
so I guess you could count, like, say you did 1,000,000 flips, right?
mm-hmm.
Then maybe you could count the number of heads in the first half of the list versus the second half, and if they were roughly the same, you would, well, I don't know if that's, well, no, that's probably not right.
But if the bias is changing for every coin.
So Orchid said we'd expect 0.5 if the bias is randomly chosen each flip. Okay, so we could make a giant, so Orchid suggests we make a giant list.
All right, let's do this.
And then we count how many heads we have, how many trues. And if the number is converging on 0.5, that means that we're getting different biases with the flips.
All right, so
Orchid says if the bias was chosen once and fixed, the ratio would come out as some other number. It's probably not 0.5. That seems like a reasonable theory to me, Orchid.
All right, so let's do this. Let's convert what's a nice way we can convert trues and falses to zeros and ones?
Well, let's see. So we're gonna have a list of hash T's and hash F's, right?
Mm-hmm.
You could just map a little lambda with an if on it. That's sort of the simplest way to do it, I guess. Lambda x, and then if x, then return 1, else return 0. And then you need a in paren for your lambda. The
Yes.
lambda body in the if.
Good call. And then, do we have some? No, we don't have some.
We can apply plus. Do apply plus.
All right.
Okay, should we try it with a bigger number?
Sure.
All right, Orchid. What do you think, Orchid? It always comes out near half. Okay, so according to Orchid's theory, we're getting different biases on the flips. So Orchid thinks the bias is fresh each time.
Yes. It is.
And David asked, couldn't we just pair the bias with the answer?
Yeah, totally.
I'm not sure what that means. What does that mean?
I think it might be something like unify, say something like make a Q, say the car of Q.
Oh, he just wants to get rid of the flip. He just wants to see all the uniforms? Is that the deal? Oh, no, he wants to have, okay. Okay, he just wants to get the X's in the query, right? Yeah. If we make X the query variable, then we should be able to tell.
Right, which is what I was kind of just playing around with.
Ah, now look at that. It's a little more complicated. So we were all wrong.
That might be that might actually just be an error in run MH.
Yeah. I thought that's how it's supposed to work. I thought it only resamples sometimes, or like all the way.
It does only resample some of the time.
So if you notice, some of the probabilities are the same. So isn't that the way the sampling algorithm works?
Mm-hmm. Yeah, so it'll resample Q, and then it'll resample X. And when it's resampling Q, it doesn't also resample X.
Okay, so there's some chance. So whenever we try again, there's some probability we'll get a new x, but it's not 100%, right?
Right. Of course, as we make this larger, for all purposes, each of them is a resampling.
So there's a reasonable probability that two consecutive flips will have the same bias, but if you have two flips 1,000 apart, they're not going to have the same bias probably.
Right. Well, all right. So what we've just shown right now, in some sense, you probably can write in any language of your choosing and just write a sampler. But this is still miniKanren. So we can have more fun than this. We can also say stuff like this. What does this do?
All right. Any thoughts on what that's about? I think I see some patterns in those numbers. Workit said you will get a larger bias when you fix hash t. Yeah, so how could we check that? How could we get evidence for that our bias is larger? Take the mean.
Seems good.
You do it with like 10,000 or something?
So
okay.
You can see the mean will converge to 2/3.
And if we set the hash t to hash f, any predictions on what we'll get for the mean?
Yes, what are the predictions?
0.33, says Daniel.
Good call.
Okay, so that's cool. That's an example of us running it backwards, right?
Yes.
So we're saying what the flip will give us, and we're trying to figure out what the probability was?
Right. So this is the probability of the coin flip. Assuming it's kind of uniform from 0 to 1.
And if we remove the uniform part, how would that change it?
Well, since we're asking for x, x needs to come from somewhere.
Oh, boo. Well,
We
you
can
can't
have
tell.
more fun. I mean, we can say stuff like this.
Okay. Can you at least like reorder the goals?
Yeah, of course. Let me just reorder the goals.
And can you put the equal q hash f first? Cool. And is that something you can do in most probabilistic languages, by the way?
I don't think you really can do that. Certainly you can't do this in Hakaru. Because a lot of the way Hakaru is set up is that Hakaru needs to kind of know what it'll do when it gets a value.
Yeah, Nahal, who has a lot of experience in this area, says no, and that many of the languages are procedural. So sort of far away from miniKanren, I guess, from this standpoint.
Right.
So I guess we're not allowed to remove the uniform because then we don't know the distribution on x. Is that right?
Yes.
Could we give x a different distribution? Do we have distributions other than uniform?
Of course. I mean, also nothing is, of course, that's stopping us from doing. Nothing is stopping us from doing that, of course.
Could we have a con-d for the x values?
Of course. I just run this just because I feel it might help you guys a bit more to see.
So I guess in this case, since we know the x, we might want to look at the q also, right?
Well, we've also unified q with false.
Oh yeah, I forgot. Okay, so I guess that's not very interesting. Okay, Orchid asks, is Condi implemented using flip? And I can
No.
answer that one, no. Condi is not.
Nah. Implementing Condi is a bit subtle. Um, um,
We've already talked about the implementation of the normal Condi a
mhm.
fair amount in the past, and one difference for people who are familiar with the miniKanren implementation or microKanren, that in those implementations, everything uses streams for disjunction or, which Condi has. In this model, we're implementing everything using success and failure continuations, which is like the really old model of miniKanren. So like the original miniKanren model used explicit success and failure continuations, and that's how we're modeling the Condi right now. But it gets more complicated because of the way the probabilities have to work, and there's a whole thing where you have to trace the probabilities, and then upon backtracking, it gets a little complicated.
So one of the subtleties, so the best way kind of encapsulating the subtleties is what happens if different branches in the Condi introduce different numbers of random variables? When we do a resampling, like how should we resample and things like that. So Condi has to do a little bit of more work in that to that extent.
The other thing is from an implementation standpoint, when Rob and I were first working on this prototype, we were still trying to figure out like how the language should work basically and things like that. So we were implementing the language as we were designing it, and as a result, the language implementation is not very clean. So at some point we need to go through and kind of overhaul everything. But I think we want to get our bugs out first, get some tests, and then sort of rewrite it.
All right. So as you can see here, through using stuff like equal equal, we can do this running backwards. And running backwards when you have not so much logic variables anymore as much as random variables, means that running backwards becomes probabilistic inference. So, and I guess so another thing is, we talked about preferences before, and I feel like so with flip we can really define that we have a preference for what Q should be. We really can say we would prefer that Q was true. We really have the ability to say that. So another distribution is normal. So with normal distribution, we can say we prefer that x be near 0. And with near, we want most of it to be within one or two of it, and then get values that are about between 1 and 2 away from 0. Just to kind of make this more clear, I'll just do this. You can see that most values are between plus or minus 1. So a lot of the power of being able to kind of create these variables from a distribution is that now we can have a preference for the values they take on, so that when we run them, certain values are more likely to occur. So I'm going to try one example. I don't remember whether this works or not, but I kind of hope it does. Is it plus O, I think? Yes.
Is this our delayed goal stuff?
Yeah, but I'm hoping it doesn't actually like trigger the delayed goals. Ah. All right, great. It didn't. We can then use these values to do some kind of deterministic computation over them. So we can do things like plus, and we can do things like plus. This isn't really quite O-like numbers at this point. Like this really does look more like plus. So a question I might ask is, supposing this was fixed, how might we encode a preference that we want R to be near 5, maybe, I don't know, maybe kind of around the vicinity of plus or minus 2. Or sorry, plus or minus 4.
So sorry, we want R to be near plus or minus 4?
We want R to be around 5 plus or minus 4.
5 plus or minus 4.
It's okay if some of them are outside that, but we want that to be roughly the vicinity.
Any ideas? All right, you may have stumped us on that one.
All right.
So we want R to be near 5 plus or minus 4. And what are we allowed to change, I guess? Only the Q and R values, or are we allowed to change some of the values in normal also?
Right. So assume that you can't change anything to the left of the blinking rectangle.
Okay, so we can only change the addition constraint.
Mm-hmm.
But we can change anything in there.
Yes.
And we want R to be 5 plus or minus 4.
Mm-hmm.
Orchid asks, will you also multiply?
Yes. You can also multiply.
Okay. It occurred to me too, like, I don't know how you do it without multiplication.
Yes.
Okay, so Orchid says we need a new intermediate value.
All right. Go on.
Okay. All right, Orchid, what are we going to do?
Going on. What are we going to do?
So we have to add something and we have to multiply something.
Mm-hmm.
Okay. I think I know how to do it. Anyone else got it? I think Orchid knows how to do it. Daniel says multiply by 4 and add 5.
All right.
Okay. So we're going to multiply Q by 4.
All right.
And then we're going to add 5 to the result. So I think here's where we need the temporary area. There we go.
All right. Well then.
Uh,
I know what I did wrong.
yeah, I was gonna ask if you had to put dot zeros.
Yeah. Nope.
Is that just a bug? What does that
I
mean?
don't know.
Can you break it down? Can you can you get rid of one of the operations maybe? Or actually, can you reify all the variables instead of doing the freshes? Can you do like Q, S, and R all being reified?
Like here?
Yeah, QSR, and then get rid of the freshes.
All right.
We can see what are getting values. Do we not support multiple run
We might not
variables?
support multiple.
Okay, well I guess you can just do like V or something and then do unification with the list of variables.
Well, I mean, anyway, let's.
Okay. So do you think is that a bug in our implementation?
I'm unclear, but I also don't want to like.
Okay.
Let's just do multiply by 4 for now.
4.0 maybe?
Yeah.
Be safe.
Just to at least kind of.
Yeah. All right. Well, that works.
All right.
And then if you add to R, then does that?
So.
Yeah.
So they vary between -5. So I'm just going to like. Is there a min or a max? Can I do like apply min for?
Do you want to do a map?
Well, I want to have the minimum with the maximum.
Oh, okay. Yeah.
So that's how our variables are varying right now.
Okay. Does that seem plausible to you?
Well, it seems to be more or less something closer to like plus or minus 8.
Yeah.
Around 0. So multiplying by 4 seems to have given us plus or minus 8.
What if you just multiply by 1? Okay.
So
Well, I mean, isn't that plausible? Because you're.
So this is the correct answer. So the way so I guess the question to ask for people is when you have a normal value that so of course this is just identity right now. Multiplying by 1 is just an identity.
Mm-hmm.
So the question I have for people is when we say normal is centered at 0 and a standard deviation of 1, where does that mean the values tend to vary?
Are you asking where you would find most of the values?
Yes.
Yeah, so which range of numbers would we find most of the values for normal 0.0 to 1.0? Daniel says about 68% of the values would be between minus 1.0 and positive 1.0.
Mm-hmm.
And 95% of the values would be between negative 2 and 2.
Mm-hmm. Yes. So this is basically the properties of the normal distribution. The way the normal works is you find 68% of your values for the standard deviation, and 95% of them 2 times the standard deviation. And this has been worked out for 3 or 4. So when people mostly characterize, when they say most of the value should be varied between here and there, what they in some sense mean is whatever you would have for the standard deviation times 2 or 3. So if you want to have things vary by, say, most of them by 4, we probably should put a 2 here. But keep in mind, the normal is defined over the infinite line, which means the normal distribution can produce numbers as high and low. Like, all values are still probable for normal, going all the way to negative infinity to infinity. But most of them, as in 95% of them, will be in a particular range. And this is actually kind of how lots of noise is modeled in the world. The noise has a particular bias, in say center is 0, and then and most of it is between this range.
So can we do a run 10,000 to see how the min or max changes for that?
Sure.
So we could expect more variation there, right?
Right. And if we kept making this larger, with some probability, a larger and larger value would be found.
And do you mind changing the times to plus? I'm just curious to see if plus is broken. No? All right. Some weird interaction between the times and plus. Okay. I'll have to remember that.
So yeah, well, what I think is just happening is I think when you have multiple determinate things in a chain, we're just not walking the entire chain. I think that's just what's happening. But that's not an error in the formalism. That's just an error in our system.
Okay.
So I know I seem to only have 10-15 minutes. I wanted to kind of show Hakaru. Before I do, does anyone have any questions about probKanren, the kind of operations?
Were there any other examples? Was the coin flip the only example you want to show?
The coin flip and basically estimating the bias of the coin flip was kind of the only example I had.
Okay. All right. Any other questions? All right, cool. Let's try moving on to Hakaru.
All right. So this is Hakaru. So the way Hakaru works is, with Hakaru, you write your programs specifying just writing different. So here's normal, and we're going to set normal as say centered at 0 with a standard deviation of 1, and then that's going to be our program. We're going to mark so in some sense this version of Hakaru is not as nice as probKanren, in the sense we have to mark which things we're going to end up conditioning on, which is to say things that we're going to write equals against. So things that we're not, we're going to write the word unconditioned in front of, and things that we are, we're going to write condition in front of. And then all the values for those things will then go into a list. This is kind of ugly and not really how things are done, but this is a fairly simple implementation. So burden on the users was traded against burden on the implementers. So this program takes center 0, standard deviation of 1, and then we're going to take 1,000 samples, and then we're going to make a histogram of it and show it. And this histogram, and we can, instead of taking 20,000 samples, we can have, or 1,000, we can take 20,000. And this, in some sense, lets you see what a histogram does. Is it takes a list, and then it basically bins the list into 20 groups of equal size, and then how many things ended up in that list end up being the height. So we took our normal distribution, chopped it up into 30 different pieces, and then counted how many elements ended up in those rectangles in that range. Does anyone have any questions?
Could you make the window a little bigger?
Oh, of course.
Or zoom in a tiny bit? Thanks. And also, can you say a few words about Hakaru for people who joined later? Like, what is Hakaru, and what's your relationship with it, and sort of what language is it based on or inspired by?
All right. So Hakaru, like probKanren, is a probabilistic programming language. The implementation I'm showing right now is an embedding into Haskell, the programming language. So this lets you write probabilistic programs using Haskell syntax, and it gives you access to a lot of the kind of post-processing around Haskell. So I'm one of the creators of Hakaru, along with Ken, Sean, and Praveen, and a bunch of other people in our lab. I should say that the version of Hakaru I'm showing now looks very different from kind of how Hakaru looks today, but the advantage of this version of Hakaru is that it's pretty easy to write in a notebook and visualize things like histograms. So one of the things we weren't really able to do when we wrote probKanren is, in some sense, visualize where the values lie. You just get this list of numbers, and it's hard to see that some numbers and some ranges of numbers are occurring more often. So when you create a histogram, that becomes much more clear.
And is this an interactive tutorial that people can try on their own?
Oh, of course. So if you search for Hakaru, you'll find the website. You can download this notebook, and if you install iHaskell Notebook and Hakaru into basically a stock Haskell installation, you can run through this notebook. This notebook doesn't use anything that isn't available in stock Haskell. So
sort of at a high level, how does Hakaru differ from probKanren? Yeah, Mark is asking the same question. So what are sort of the strengths and weaknesses and perspectives of the two languages?
So the big advantage with something like Hakaru, at least what I'll be showing right now, is that it's embedded into Haskell. So if you recall, we went through a lot of effort to do things like plussing and times, and if I want, I can just do this is a perfectly what is it? Why is it not happy? Oh, sorry. Wait. Too much time and scheme. And if you'll notice, we're centered around a different location and a different range.
So can you put arbitrary Haskell code inside of a Hakaru program?
Within reason, yes.
Okay, so clearly that's one difference. You can't just put arbitrary scheme code in a probKanren program any more than you can put arbitrary scheme anywhere in a regular miniKanren program.
Right. So that's one advantage of Hakaru, is that for the most part, almost any kind of operations you want to do on these random variables, you can. So one of the other things is we actually define this a kind of a probabilistic monad, so we can kind of bind out. We can actually kind of do arbitrary operations on these things. So another way this program can be written, which I'm going to just do right here. We can do test 2. We can say take a sample from X and return two times X plus 5. Sorry, this is just something that's just taking the average. I didn't do the histogram. But as you can see here, once we take a value from X, we can do arbitrary operations to it. The type of X here is not a distribution over real numbers. It's just a real number. So any part of Haskell that deals with doubles can be put here.
And presumably you could define your own functions and call those. And
oh yeah, of course. Yeah. So we can just do we can define a function. As so, and then just so any operation can happen. This is kind of an advantage of Hakaru, is that we can just treat values from these distributions like any, we can basically, once we bind something, which is to say I'm talking about the distribution such that for every single value in this distribution, do this operation to it. And we can use that to transform to different programs.
Very nice. So do you have a slightly more complicated example you want to show us?
Sure. So let me actually go through polynomial regression. So I've just made this plot here, and just to kind of show you the data, this is just what the data looks like on X and Y. It kind of has you'll see it has a shape to it. So one thing we can do is we can actually write a probabilistic program to infer the best polynomial that fits that shape. So we can say we want a normal distribution for the constant term, the linear term, the quadratic term, and the cubic term, and then we can then sample for each of the number points we have a polynomial over them, and then ask for what those weights are. So hold on, let me just. And then we can draw a curve through what curve we think best represents those points. So
how would you contrast this approach with using a package like R or a language like R or Mathematica or MATLAB? So what are the trade-offs, do you think?
So one of the trade-offs we have here is that when you use those packages, you don't write the inference. You just get whatever inference is there. So when you perform linear regression assumes a normal here. If you know a little better, like if you think another distribution over the values makes more sense, maybe something with heavier tails. So because like one of the things you can do is you can have something like, say, the Laplace distribution. So I'm just going to type it. I can show this in Hakaru, but I want to show this here because I want you to be able to kind of look through what different distributions look like. So A 0, 1 Laplace distribution, you'll see here, is much more sharply peaked around 0 and falls off much more rapidly down to the other values. And of course, you can make it more gentle, but you'll see it's very sharply peaked at 0.
As opposed to a bell-shaped curve or normal curve.
Exactly.
Nice and smooth.
As opposed to the bell-shaped curve. Actually, let me just quickly check if this will work. So if I put in here, you see, much more sharply peaked. So we can modify that if we have like these, if we think the value varies in that way. You can't really do that with an off-the-shelf package. You kind of have to go with their assumptions. If you don't really know what assumptions you should be making, the package can be better. But once you have a feel for your data and how the different parameters vary, you can do much better. So this is also a pretty big block of code. You know, this is kind of a pretty harsh transition because I'm going from a 2-line program to like a 15-line program, which can be a bit jarring. So I know we're 5 o'clock on the dot, but depending on how much extra time people have, I'm happy to like go through extra questions with just this program right here.
Okay, yeah, we got a few more minutes. Any questions about this program? Can we see it run, Orchid asks.
What do you mean by see it run?
So that plot you're generating is the output, right?
Yes.
Okay, can you bring up the plot again? Yeah, so that's the result of running that snippet of code.
Mm-hmm.
If you wanted to see, okay, so that's one output. If you just wanted to see the numbers, like the polynomial, you know, the actual constants for the polynomial, can you look at those also?
Yeah, sure. Let's do that. So yeah, that sounds fine. So basically what we're going to do is we're going to sample from this probabilistic program, conditioned on the actual values we got out from the y. And then what this program does is it takes the mean of these values. But let's not take the mean right now. Let's just return the values. So this is each sample. And you'll see there are 4 arguments in here. Maybe I should print out 10 values instead. Is my Haskell misbehaving? Oh, I see what it is. What the? What was that?
Yeah, pro tip: if you're gonna troll, don't name your account Chaos Streak.
All right, so.
Okay, so can we see the tug of war or something like that?
I actually thought I had more time, and I thought we would write tug of war interactively. So.
Oh well, no, we've got some more time.
Well, all right. Let me first
Yeah, I mean we could take like another half an hour or something. I mean, if people have to leave, that's fine.
All right. Let me just I just restarted things, so I just want to make sure that All right. All right. So let's just try. I didn't define mean. Here it is. All right. So let's just. I just wanted to show.
Orchid is wondering, what does that 15-line program do? Is it generating points on a cubic curve?
No, it doesn't. Let me just. Haskell can be a little bit finicky when it runs in the notebook, so I just want to make sure I do this. All right, so here. All right, there we go. So just to explain what I did. With Hakaru, because we're a nice lazy language, MCMC just returns an infinite list of samples, which we can then take from. And I just decided to reply in turn and return an infinite list of samples, which doesn't really do us too good and clogs up on my CPU. So I'm just returning 10 samples here, which you can kind of see. So let's look at this program again. What we do is we have these 4 points, which are the coefficients. And then what happens is we feed these coefficients to a polynomial, to a function called poly1d, which essentially takes a value x, a particular value of x, and then multiplies it against the polynomial that's represented by these 4 numbers, which is then what we condition on, because that's what we say the y value came from. So we're not actually sampling values on the curve. We're sampling coefficients of a polynomial. But it's hard to visualize polynomials as like these 4 numbers. So instead, what we do is we take their average. And then visualize that as a curve. And that's essentially what that's essentially what we then do with chart. What chart will do is it'll take these 4 numbers and then create a polynomial from them.
So instead of generating points on the cubic curve, we're actually generating cubic curves and then averaging over all of them to get us a single cubic curve that's sort of the average of each of the individual parameters.
Exactly. So,
and this I guess gets back to Olivia's question about trying to fit parameters, right, for a function.
right.
So we're trying to find the right parameters for this polynomial.
Precisely. So we can go through all these, and also keep in mind we can make this code simpler. So again, because we have access to Haskell, and these probabilities come from a monad, we can actually. I messed up again.
Do you keep generating infinite answers?
Yes.
Welcome to my world.
Well, generating infinite answers by accident.
Yeah, like I said.
Um, so let me just. So what happened? So what we can actually do is using this using replicating, which basically just says run this 4 times. We can actually just create this list of this 4-element list that just each one is just sample from normal 0 2, sample from normal 0 2, 4 times. Um, uh, but this is in some sense what the power of probabilistic programming is, that you can define where you think where you think the parameters for this curve come from, but you can also say, well, I know that those points came from I have these data points already, these x's and y's. And that's in some sense what this normal is here for, because our points don't exactly come from a curve. They come from a curve with some noise added to it. It's like, the center probably this. So what we're really saying is these points didn't come from this curve. The points I'm giving you didn't come from the curve. They came from the curve with some noise added to them. Their center is where the curve is, plus or minus 2.
So I guess this is where the art of modeling comes in, where you're trying to understand or specify which distributions you have on different parts of your program.
Mm-hmm.
And that takes some human domain expertise, presumably.
Right.
So Orchid asks, if you had a few thousand points, can you find the coefficients from that? Since right now it looks like coefficients are generated, then points generated from them. Or
Well,
you're starting the other way, right? You're starting with a bunch of points, and you're trying to find the curve that fits those points the best?
yes. So we actually start with the points, but we write our program in such a way as if to say that the curve generated the points. So I put here, I don't know, I think it's something like, I think I have something like 50 points here. But in principle, this is just a Haskell list. I could have just loaded these from a file, from a CSV file that has millions of points in it. And nothing about this program down here changes.
Okay, so Orchid didn't realize there was data. So you have data, you've got a file of points, and that scatter plot, if you can bring the scatter plot back up, so the scatter plot are the data points, right?
This is the actual data I've written in. These did not come up from a program. These could have come from a file, the internet, anywhere.
And for some reason, maybe based on domain knowledge, we think that there's some sort of polynomial, a cubic curve or whatever, that will match that data. And you can kind of see it. You can kind of trace it out with your finger what the curve might look like. And we're trying to infer the best parameters for that polynomial.
We're drawing that curve. Yeah. So in some sense, what we can view is we can ask this program as, give me the best curve, find me the curve that fits these points closest.
Okay.
But it's so much more natural to just say I have a curve, and it drew the points. By the way, I'm going to unify the points it drew with these points that came from a file. With these points that came from a file, which is what condition dot does. In some sense, it says these y. This is kind of a very ugly way of writing this, which is kind of one of the reasons that Hakaru changed since this style was written. We kind of say all the points, we're going to unify them with the y values. Because when we generated these points, we know they actually came from this file. And what should the points be, given we already know this?
All right. Well, Orchid's very impressed. Orchid didn't realize that it was based on data.
Right. And We can do fancier things as well because we have access to Haskell. And feel free. This is if you search for Hakaru online, you'll find this notebook online. And we could do fancier things still. So we can do things like just discrete distributions, which we can automatically create bar charts for. We can do outlier detection, where we can detect what points are the outliers and where the curve is. And that program is actually also fairly short. We basically say either a point came from an outlier or it didn't. And we can do distributions over arbitrary data structures, data types. And there's feel free to look through this later. Using the remaining time, I actually think it might be better if we actually I'll put it here. We wrote an example together. So I like to write an example, which is actually very classic in probability, which is we're going to model tug of war. And the tug of war example is very interesting in the sense of it kind of can model almost any game once it's been generalized. But we're going to assume that we're going to have a situation where we're going to assume that we have a person, Alice, who has a particular kind of latent strength. And we have a person, Bob, who also has latent strength. And then they're going to play a game, and how strong they pull is in some sense based off their latent strength. And then whoever pulled stronger wins. So how would we write this in Hakaru?
Any ideas? Any suggestions? Orchid says a coin flip. A biased coin flip?
Of who wins the game?
Of who wins the game? Yeah, I guess that would make it really simple, right?
Winner. So winner is equal to a biased coin flip. I know what Orchid's doing, and I actually really love this technique, but it's a little. Oh, let's go with it. So we're going to say.
So Orchid has a snippet of code. The winner equals Alice greater than Bob. I guess it means if Alice's strength is greater than Bob, then Alice is the winner.
Okay.
Okay, that's very similar to what you have. Okay, what else would we need in this program? Where do these strengths come from?
Yeah, let's do that. Let's actually do that first. Where do the strengths come from? Let's pick a distribution.
I think you're missing an R in strength. Yeah, so I think the standard the model for this is that you have people who each player has a certain strength, but then each day they might be a little stronger or weaker, right?
Right. You don't pull with the exact same strength every time you play the game.
So if you ate your Wheaties in the morning, maybe you'll pull a little stronger.
Right. So how should we model Alice's strength?
Any thoughts? A normal distribution, says Daniel.
All right. What should we center it under?
I guess it doesn't really matter so much. Something not 0, probably.
All right.
Right?
We'll center it at
Like
100.
positive.
And we'll do this.
Okay.
And what should we make? What should we do for Bob?
Yeah, how strong is Bob? Is Bob a strong man or a weakling?
Now's not the time for gender normative opinions either. You can be whatever you want.
Let's make Bob a weakling.
All right. Sounds good. All right. Where do we go? Okay, so now they're going to pull. So they're each going to pull from the distribution. What happens now? Now we have numbers.
Okay, so Alice and Bob, those are the actual strengths they're pulling with for this particular game. For this
Right.
particular instance of the tug of war game. Okay. And can we just do what Orchid said and
Yeah. We can do
Alice
that.
is good and Bob?
So we can do Alice greater than Bob, and Alice wins. Else Bob wins. And then we can, of course, now what's the type of winner? Give me a moment. There we go. Let's go back here. All right. What's the type of winner? Measure over strings. So
So what's the measure? Is that going to give a probability?
it's a distribution over strings. So meaning now we have this object, we have this program. So let's sample some results from it. Let's do that. So to do that, I'm going to sample from winner.
And MCMC is one type of sampling?
Yes.
You could presumably use other types of sampling, right?
Right. Now we're going to return 10 samples. All right.
Well,
So
Alice wins a lot. Maybe Bob's a little. Maybe we should need to make Bob a little stronger.
all right, let's make Bob a little stronger.
Okay.
Bob wins sometimes.
Bob just won once.
Twice. He won twice.
Twice. Okay.
He won twice.
Well, I guess we give maybe Bob more variance. Make him weak, but have more variance. Would that help?
All right, so we can do that.
Wow. Wow, Bob wins a lot there. I guess it just depends what direction he goes, right?
Right. So this is all well and good. Now, so the question I have now is what would what if we didn't know their strengths?
So metaphorically, we're running this program forward, right?
Mm-hmm.
We're running the simulation forward, and now we want to run it backward.
Right.
Yeah, so Orca said that would be really interesting.
All right.
Okay,
That's
so
good.
instead of the unknown being who wins, the unknown we'd know who wins, and the unknown would be part of the strength, right?
Right. Let's write this program in a slightly different way right now. I'm just gonna do this because it'll make another part easier. Which is, let's try it. Was it Daniel who suggested this way? I'm gonna write this program. I think this will work. All right, so I have this function here called logistic, which I'm gonna run. So all logistic does, just to kind of be clear, is it maps things from the real line between 0 and 1.
What?
Hmm?
What does that mean?
This is just a function that basically maps things from negative infinity to 0 and 1.
Okay.
And it maps 0 to 0.5.
So the closer we get to infinity, the closer we get to 1. The closer we get to
Right.
minus infinity, the closer we get to 0.
Right. So what we're going to do now is we're going to replace this with Alice minus Bob is going to go to logistic. I'll return that.
Is this that log linear probability stuff?
Somewhat. Let me see. So now basically when the number is close to 1, it means Alice won. When the number is closer to 0, it means Bob won. So Alice won, Bob won, Alice won, etc. So one of the reasons we're going to do this, we're going to do the suggestion of now we have kind of like a soft value with number that varies between 0 and 1. And what we can now do with this value, just to give it just to make this easier, is we can now say something like flip W. And now get trues and falses out. So why did I make this change?
Presumably so we could run backwards?
Well, yes. What's the advantage of this change?
I don't know. Can anyone tell? Daniel said, hard to do anything learning-wise without a gradient. Well, that's true. But we could run backwards. Well, yes. What's the advantage of this change? I don't know. Can anyone tell? Daniel said, hard to do anything learning-wise without a gradient. Well, that's true.
So that's one of the reasons.
Orchid said you can add the results together. 10 wins.
So that's one advantage. Now we can just we can do things of that sort. The other advantage is that by putting things into, it's hard to condition on, in this version of Hakaru, it's very hard to condition on strings and just saying, by the way, this whole thing here, this if Alice greater than Bob, then this, it also actually turns out to be kind of ambiguous what that means. So do we mean that Alice minus Bob is equal to 1, or do we mean that Alice minus Bob, do we mean Alice minus Bob is greater than 0, or do we mean Alice divided by Bob is greater than 1? These actually mean different things. So it's a bit ambiguous, and so when you try to condition it, Hakaru's not really going to know what to do. So by putting into logistic, by saying Alice minus Bob and putting that into logistic, we now have a value that we can pass into, this is essentially flip. We just called it a different name in Hakaru, and get the value. So one of the things we can...
I'm trying to understand the intuition. Is the idea that we want to keep track of by how much Alice beat Bob?
It's more that, like, when we say Alice beat Bob, like, numerically what we mean is a little bit ambiguous. So by making it explicit that we mean that the strength that Alice's performance is this linear strength, by making it more specific, we're just removing an ambiguity from the system by writing it this way.
Okay, so we're deciding on a linear model versus some other model we could pick?
Exactly.
Okay. So this is where the expertise or the art of modeling comes in, I guess.
Right. Now we just, so let's now say we actually know whether Alice won or not. So we're going to take this unconditioned, turn it into conditioned. And we need to put in here that Alice won. The way this is done is using this really ugly thing that we've since removed from Hakaru, but we still have here. So lots of apologies.
Okay, so there's some magic going on, and we don't have to know every detail. We're just trying to understand what it is you're able to do with this model.
Right. So I'm just going to make this easier, just put these here. Alice wins. And now I can just put Alice wins here. Just know that this is just wrapping to make Haskell happy and has nothing to do with the concepts. So we can say now Alice wins.
So that's a single outcome?
Right. It's for a single outcome. And now when we say this, why is it being angry at me?
Language spelled wrong.
I misspelled language. It's always true because
Alice won.
Because Alice won. Well, let's not. How can we? So, how would you change this program?
Okay, so right now Alice always wins, but that's kind of boring.
Right. What's something else we can ask?
So what are we seeing? What are these falses? Is that showing Bob winning?
Well, yeah, that's showing the Bob one.
Okay. And yeah, Orchid says we want to get a pair of their strengths. We want to see what their relative strengths are based on the result.
All right. How would we do that? Remember, you're allowed to use arbitrary Haskell here.
Eugene says, can we make produce the chance of a result? Yeah, so we want to get the probabilities of the result. So Orchid says, can we return Alice, comma Bob?
Yeah, totally. Here's some samples of their strengths.
Okay. Now, can we actually put in some unknown values in the distribution and infer that? Like, what if we didn't know Alice was normal 110?
All right.
If we
How
had
might
a
we do
bunch
that?
of logic variable?
All right. Let's go for it. What do you want to put in here?
Fresh X.
Well, you don't have to put fresh X here.
Do we have to put
in a
anything in there?
distribution.
Why do we have to put anything in there? Oh, we have to condition it on. Wait, do we have to put in the results of the tug of war or something?
No.
I don't know what goes in unconditioned distribution.
Yeah.
Well, what do we have to give it a distribution? Are we gonna like infer that? No, we have to put a distribution
We can't
on all the
infer it,
variables.
but we have to start somewhere first. We have to say what domain values we're looking over.
Fresh logic variable. All right, that doesn't fly, huh?
I mean, nothing is stopping you from saying, oh, we think it's between 0 and 1 uniformly.
Okay. So, all right. So this is where we have to guess what we think Alice's strength is.
Mm-hmm.
Roughly.
So in some sense, we can still consider what we have here an initial guess. So we can initially say that we think Alice's strength is 100 with a variance in 10, and so is Bob's. And this kind of will still work as an initial guess. In fact, let's scroll. My apologies while I scroll back. If we look at the samples we get, nothing is stopping us from, say, where do we go? Say, taking Alice's strength. Let's see if this works. Why is it being annoyed? Let's see here. Ah, yes. So let's put a few more samples here.
Okay, so we're seeing for 1,000 trials how often analysis strength or in these
Yeah,
different ranges.
right.
Okay. And that's based on Alice winning every time, is that right?
That's based on Alice winning once.
Been winning once. Okay. So what if we had, like one of the simulation outputs where sometimes Alice wins and sometimes Bob wins? Can we feed in a list or something like that? Or a probability or something like that?
So this is what happens if Alice wins twice.
Okay.
Change a little bit. So we can now
So the more often Alice wins, the stronger we're going to infer her strength to be.
yes. Let's of course now look at Bob's strength. I wish I had a nice way of overlaying these two charts so you can kind of see them side by side. But you'll notice that Bob's strength is a little lower than 100, while Alice's is a little higher than 100.
Okay. And if we made Bob win a few times, okay, so Alice's strength has gone down. Now it's a little less than 100. And how about Bob's strength? Okay, so now Bob's strength's above 100.
Mm-hmm.
Okay, so we're really running backwards. We're saying what the results are of the competition, and now we're using that to infer what the strengths were initially.
Precisely.
Eugene wondered how much work would it be to have the backward run produce the chance of the outcome. I think, if I'm understanding correctly, without sampling, I guess you're trying to say, Eugene, could we say what percentage chance Alice has of winning, or Bob has of winning? Yes. Okay. Yeah. So what if we wanted to get a probability that Alice is going to win? I guess that'd be more running forward than backwards.
So one thing we can do is we can do Alice minus Bob. So we can ask kind of, given we've seen Bob win twice, what are the odds in some sense that Alice will win? Keep in mind, this isn't a probability that we're going to return. This is just our estimation of Alice's strength minus Bob's strength. So it's kind of our estimation of their difference. We could do that.
That's an interesting shape. It's like half of a bell curve.
Mm-hmm.
Is that to be expected?
Mm-hmm.
Why is it half a bell curve?
Because in some sense, most of their mass is in roughly the same area. Also, a lot of it is that because Bob is 1.
Oh, so we have more confidence that that Bob is stronger than Alice than we do that Alice is stronger than Bob. That's why the asymmetry is there.
Yeah. And then if we, if I flip them around, make it Bob minus Alice, you'll see.
So from that, is there an easy way to generate the probability that Alice is going to win or Bob's going to win?
So a question I ask is, of course, how might we generate whether we expect Alice and Bob to win or not?
Wait, sorry, say it again.
So one thing we can do is, how might we generate that chance of Alice or Bob will win or not? Like, how might we get that value? Because another way of viewing this is we can simulate
So can
another
we
event.
can we just count? Can we just do like 1,000,000 samples and count?
So yes, we can.
So I guess Eugene is wondering if we can do it without sampling, but I guess let's see how we would do a sampling first.
So one thing we can do is we can do this, and that's kind of we can say. I made this great. There's a primitive in Hakaru that I want to make use of, which I think I defined here. Yes. All right, let's go back. Ah. All right, let's try this one more time. So,
whoa, that's pretty hefty.
So we did 10,000 simulations of whether Alice or Bob wins, and then most of them, Alice doesn't win. We observed that Alice won once and Bob won once. Here's what we see. I'll make it 100 just to like.
So when we have few samples, it could go either way. But the more samples we have, the more likely it's going to be even, right?
Right, because we're getting because we ran the simulation longer. This is actually very similar to the kind of things you see when like say 538 or other forecasting places predict election. They say, given everything we've seen and know, when we simulate the election, 50,000 out of 100,000 times this event happens. 10,000 out of 100,000 times this event happens. This is in some sense what they're doing.
Gotcha. Okay, well, why don't we start finishing up here?
All right.
Does anyone have any questions about anything you've seen tonight, or the probKanren or Hakaru or probabilistic programming in general? Could we do these sorts of notebooks for probKanren?
I think so. The larger question is, can we do these kind of notebooks for Scheme?
Well, so what about Church? I mean, Church has these sorts of notebooks, right?
Somewhat. not quite there. The one that really has these notebooks is a one called Anglican, and it uses Clojure, and Clojure has a thing called Gorilla REPL, which essentially lets you do these sort of things.
Okay, so any Clojure should check out Anglican.
Right. If you like Clojure, there's an implementation of a probabilistic programming language called Anglican for Clojure. It's written in a different style than either probKanren or Hakaru, but the basic ideas are still there. One of the things I kind of prefer about this style is you can kind of write your program once, and then the parts that are conditioned or unconditioned, you can kind of almost leave for later. In fact, in later Hakaru, the current Hakaru that I'm not showing you right now, these unconditioned things have been made to go away.
So if someone wanted to learn more about this stuff, so say that you find this really interesting, but you don't know anything about probabilistic programming other than what we just learned, and maybe you don't have the strongest background in probability theory. What resources would you suggest?
So the resource I suggest right now is a thing called ProbMods, and it's an interactive textbook that kind of goes through probability modeling and probabilistic programming, and I think it's pretty nice. One nice thing is also is that you can run these different simulations and kind of get a sense for how different probabilities work. So yeah, they have things like a simulation of a pachinko machine, and they also have Church, which you can also run from the examples.
And this would be a nice intro, especially for folks who are watching these videos, because Church is basically scheme with flip and a couple other probabilistic primitives. So you're already familiar with the syntax and the basic language.
Right. Now keep in mind, Church doesn't, and a lot of them, Anglican as well, they don't really have this notion of logic variables. So if you notice in Hakaru, there's almost I have something almost like a fresh Alice. I have this logic variable I can use and kind of move around with. There, it's very you have to be kind of careful with how. So it's hard to say do multiple things with the same logic variable and be able to talk about it. So you have to be a little careful, but the tutorial goes through that fairly well. But if you want to play around, that's what I would recommend. There is a book from Manning on probabilistic programming, but I don't think it's actually out yet. I think it's still in early access, but they talk about things as well. But I think for the most part, I would suggest ProbMod.
It's a good place to start. Thanks. Orchid has a question. What are some things that have been made in Hakaru? What sort of programs have you written, or what sort of systems or whatever?
So I haven't really written systems quite yet. In some sense, these last year or so, we've really been spending more just kind of evolving the language, so we haven't really written anything big in it. Kind of the coolest programs we've written are all things in this kind of notebook. So if you went to indiana.edu/PAML, you get our homepage, and you can get the notebook, and you can kind of browse through what we have here.
What sort of programs would you like to be able to write when Hakaru becomes a little more mature?
Basically, I'd like to be able to do serious natural language processing application. I'd like to be able to do things with computer vision. I'd like to really be able to do the kind of things where classic machine learning is used, and kind of move beyond a lot of these toy programs.
And will that require making Hakaru more efficient?
I don't know if Hakaru needs to be made more efficient, but it might entail moving beyond naive sampling methods and things of that sort.
David Kahn asks, how does Hakaru differ from Hansai, which was the system that Ole Kiselyov worked on, right?
So Hansai does exact inference, so it kind of suffers from the same things as, say, miniKanren does, where it's harder to do things over real numbers.
Okay, so it's good for discrete.
It's good for discrete. It's good for discrete because it'll compute them exactly, and it does some nice kind of memoization so that you get some dynamic programming benefits.
So this would be like what Eugene was asking about. Could you calculate the probabilities without sampling? You do that in Hansai, is that right?
So a program like this, written in Hansai, might work, assuming that assuming we made these distributions a little bit more discrete as well. So instead of say Alice having a distribution from a normal, we might say Alice has, we might make it more. We turn it into bins, and we say with probability 0.1 we think Alice has this strength. With probability 0.1 we think Alice has this strength. You could do it as well.
Orchid asks, could you train your own Google Translate using Hakaru?
Right now, no, but I would love to. And I mean this in the most seriousness of terms. I would love to make it so that I could just trivially write a program in Hakaru that does translation.
Do you think that'd be feasible? I mean, if you had like access to a big cluster, could you distribute it or things like that? And, scale it up.
It's not just parallelization. It's that so the problem with sampling is that you have to go through your entire data set over and over again. It'd be nice if you didn't have to do that. Because if you think about something like the curve, so I think the curve example is really good for this. We have 4 numbers we're trying to guess. We don't have 50 numbers we're trying to guess. And it'd be nice if we didn't look over the entire data set. If instead we guessed I'm actually going to turn off this screen just to kind of like show my face because I'm making lots of gestures now.
Okay.
So, oh man, a completely new, different set of people. I hadn't looked since the beginning. So if you have 4 parameters you care about and you have 50 data points, that's fine to loop over all 50 and kind of see how well those 4 data points explain, how those 4 parameters explain those 50 data points. But if you have 1 billion data points, it makes much more sense to say subsample a bunch of them and see how well it explains them and sample in that way. So even I think the sampling algorithm needs to be changed a little bit as well to just make to be more efficient. Because I think it's insane to say, because if you noticed, we don't really get good answers until we say sample 5,000, 10,000, 20,000, 30,000 results. So I don't think it's if you have like a few gigabytes or a few terabytes of data, iterating through that 30,000 times is a bit rough. So we also do want better sampling methods as well. One of the advantages, though, of probabilistic programming, and this is the advantage I cite for other people, is that those improvements to the sampling algorithm do not involve any changes whatsoever to your actual programs. That's all can happen internally. In some sense, we just have to write run to be a little smarter. We change run. We don't change normal or uniform. None of that gets changed. It's run that changes.
Very cool. So you can write one program, change the sampling algorithm, and get different behavior.
Right. I don't know if you see that as a good thing, Will, or not.
Well, it reminds me in miniKanren of how you can write a miniKanren program and then change the underlying search, right? Because there are lots of ways to do search, and you'll get different results. And there's no like right search, like it's all different trade-offs, right? Okay, very well. Well, I think we're hitting the 3-hour mark.
All right.
So, I think we could probably take one last question if there are any. Otherwise, we'll call it a day.
All right.
All right. Okay then. Well, thanks very much, Rob. This is a very interesting style of programming, and I hope people will check out Hakaru and the ProbMods tutorial.
Thank you for
And
having me, Will.
oh yeah, definitely. Our pleasure. And of course, there's probKanren. Hopefully, that will get into somewhat better shape in the near future. So thanks a lot, and I will turn off the broadcast if people want to hang out and ask any questions afterwards. That's cool. Otherwise, I'll see you all next week. Stopping the broadcast.